Section 5.1 is the introduction to indefinite integration, also known as finding the antiderivative of a function. Recall, if f of x represents the exact value of a function, then f prime of x is the derivative, so that's the instantaneous rate of change in the function. All right, next, let's say that capital F, big F, how about if big F of x is said to be the antiderivative of little f, okay, that means that big F prime of x equals f of x. Big F prime equals little f, all right? Once again, big F is the antiderivative of little f, okay? Big F is the antiderivative of little f for every x in the domain of f of x. The process of finding an antiderivative is called antidifferentiation, or for short, we're going to call that integration. Okay, integration. It's the same as antidifferentiation. It's the opposite of taking the derivative. So what we're going to do now is we're going to repeat what we've said there, and we're going to write it in a different form and come up with a process. So I'm going to repeat, I am going to repeat that line right there, and I'm going to change the notation. So instead of big F prime, I can write that as df dx. df dx means the derivative of function big F with respect to x, right? So that's all I've done so far is I've replaced the way I've written that particular notation. All right, so we simplify that. In other words, we multiply both sides by dx. Multiply both sides by dx. Here on the left, here on the right. And that gets you to the next line. Okay, so next we take the antiderivative of both sides. The antiderivative means it cancels out the derivative. Now this little d right there and right here, that means change. Okay, it can also stand for derivative, right? And so if I take the opposite of a derivative, they cancel each other out. And now you just have big F of x. All right, I did that on the right-hand side too. And on the right-hand side, I've got this funny looking symbol in front of little f. That little symbol is called the integral symbol. You see that right here. It's called the integral symbol. Brand new information for us right now. It's the opposite of a derivative. So the integral is the opposite of taking a derivative. The integral symbol, the integral is the same as the antiderivative. All right. Now, this line right here tells us that for a reason that we will explain shortly, we need to add a constant c, right? So to f of x. So when we find big F of x, by taking the integral of little f with respect to x, I have to add a constant c to my answer. Add a constant c to your final answer. All right. A little f of x in that position on this line right here. Little f is called the integrand. X is your variable of integration, and c, like I said, is our constant that we will add to our answer at the end. So this brings us to this theorem that you see here. If big F is an antiderivative of the continuous function little f, then any other antiderivative of little f has the form of whatever that antiderivative was that you were given, plus c. All right, there's that adding the integration constant. And so what that's giving you is an entire family of functions, the g of x family of functions. And that family of functions takes this basic function, big F of x, and it keeps adding different c values, different constant values. And all of those put together gives you a big family of functions. They all look very similar to one another, but what sets them apart is the different adding, the different constant that you're adding to each integral f of x. All right, so for this example, to see how this theorem is put together, we have big F of x equals x cubed. This is said to be the antiderivative of the function f of x, little f, which is equal to 3x squared. In other words, if I take the derivative of big F, if I find big F's derivative, I should get little f. And if you check that out real quick, you'll see that you do. If you take the derivative of x cubed, you get 3x squared. And that's what makes big F the antiderivative of little f. All right, so we can write our answers as a family of functions. We call that family g of x. Remember, g is my family. And so g of x is made up of the integral of f of x, little f of x dx, which once again, little f is 3x squared. Just put that in that spot. And so when I get my answer, I get x cubed because after all, you were told that that's what that's what you should get. Big F was x cubed. But then we add this integral constant, the constant of integration, that plus c, and we get our whole family of functions. C can be any constant value you want it to be: positives, negatives, square roots, fractions, decimals, rational numbers, irrational numbers, anything you can think of. And so all of the graphs of this family of functions of G are just vertical transformations of one another, because whenever you add a constant or subtract a constant, it moves that basic function up or down. All right, that's a lot of background details about anti-differentiation. Let's see how it actually works. There's a whole bunch of rules that you can pull out of your book. I am not going to bore you with the rules because I think it makes more sense if you see how they work as examples. But if you would like to go through and read the rules, those are where you can find them in the book. Now, the integral is the opposite of taking a derivative, right? Keep that in mind. So I'm going to first change this to say 2 times the integral of x cubed dx. The integration does not affect a factor that's a constant. So that 2 times x cubed is not going to change your integral answer. So I'm going to bring that out into the front so it's out of my way. Now I'm taking the antiderivative of x cubed. So that means it's the opposite of what you would have done had it said take the derivative. Had it said take the derivative, you would bring the 3 down in front, lower the exponent by 1. So we're going to go backwards. We are going to increase the exponent by 1 and divide by that number. We increase the power by 1 and divide by the number that is that power. We want to include our constant with our answer, and we want to simplify. So I'm going to write this as 1/2 x to the 4th plus c. And that is the antiderivative of 2x cubed. Now we can check our answer. I'll do this maybe once or twice, but I'm not going to check all of my answers. But here's how you could, until you're confident that you've got this. You could take the derivative of your answer. Take the derivative of that answer. And so if I take the derivative, find the derivative. Let's call this g, okay? If I take the derivative of g, I would bring the 4 down in the front, multiply by everything that's there, lower the exponent by 1, take the derivative of c, which is 0, put it there if you want, and simplify. This would be 2x cubed, right? And so now you see that that answer matches what you had. And that's what you should get when you check your answer. Those two should match. Let's try it again. We have a whole bunch of examples, so you get the hang of this. All right, so another property of integration that you'll see if you read through those rules in the book is you can take the integral and split it across a plus sign or a minus sign and do separate integrations. I could have written that as a minus right here, which might make more sense, so let's just do that. All right, so I just chopped that integral into separate integrals across that minus sign, which is one of the rules that you are allowed to do. I'm going to write 1 over x squared as x to the negative 2. And x cubed, I'll write that as x to the negative 3. And so when I take the integral, it's the opposite of the rules for differentiation. So had this said to find the derivative, you would bring the exponent in the front, multiply by what's there, subtract 1 from the power. We're going to go backwards. We are going to add 1 to the power and divide by that number. All right, same thing on the next integral. We were going to add 1 to the power and divide by that power. There's your plus c. Okay, so I'm going to change the way this looks. Negative x to the minus 1 plus 1/2 x to the minus 2 plus c would be how I would write my answer. And if you didn't like the negative exponents, you could put those in the denominators, but it should be fine. One thing I want to stress is that when you're doing the homework for 5.1 in Connect Math, if you forget the plus c, it'll be counted wrong. So don't forget the plus c. Don't forget plus c. It doesn't matter if you use capital C or lowercase c, but it's got to be there. All right, next one, we are going to separate this into separate intervals. I mentioned checking on the first example. You could check this as well. You could take your answer, you could find the derivative, and you're going to get, so if you take the derivative of this function, you're going to get that for your answer if it's correct. All right, so we're taking the derivative piece by piece. I'm going to split this into 3 separate integrals. I'm going to rewrite the square root of x cubed as x to the 3/2 power, just to save me a step on the next line. I'm going to write this as minus 1/2 times the integral of x to the minus 1/2 power. Don't forget your dx. And then plus the integral of the square root of 2 dx. All right, so I just rewrote the terms a little bit to make it more convenient to take antiderivatives. So x to the 3/2, you add 1 to the power. You divide by that power. Next, you add 1 to the power. You divide by the power. Next, what's going on here? All right, whenever you take the integral of a constant, think about when you do your check statement or your check step. If you have a term, okay, you have a term, and you find the derivative of that term, what would that term need to look like for its derivative to be the square root of 2? What would the term need to look like in order for its derivative to be root 2? How about that? Root 2x. If you took the derivative of root 2x, what would you get? You would get root 2. And that's the way to check. All right, simplify just a little bit here. Dividing by 5/2 is the same thing as multiplying by 2/5. Dividing by 1/2 is the same thing as multiplying by 2/1. Now, when I multiply 2/1 times 1/2, I just get 1. So that would be my answer. And I would check if I wanted to by taking the derivative, and I would get back what I had in the integral.